Damascus steel. It's one of those legendary things. A sword that could slice a piece of silk in the air, but also shatter armor. It's a mystery, but the secret isn't just lost art. It's forgotten science, and by the end, you'll see how a medieval weapon, it accidentally created nanotechnology. 1,000 years before we had the word for it. How did they do that? Ancient blacksmiths, just fire and hammer. They made carbon structures we can hardly build in labs now, and the clues in those blades, they could change materials forever. When you imagine a leap in technology, how far back does it go? The sound was something you couldn't forget, not just a clang, it was a sharp, clear ring. And then a terrible silence. On a medieval battlefield, a European knight would see it happen. His own blade, made in the finest forges of his continent, would be sheared clean through. And the weapon that did it seemed to dance with light. The swords from the Near East were different. They were beautiful. Their surfaces had these swirling patterns, like flowing water or rippling silk. We call that the damask pattern now, named for Damascus, a trading hub where these blades became famous. But that beauty wasn't decoration, it was a signature. A mark of supreme function. The chronicles from the Crusades are full of accounts. They read like technical reports. They say these blades cut through the mail armor of European soldiers. They say the blades were so resilient they could bend nearly double and spring back true. There's a persistent legend. Travelers and historians like the Arab chronicler Ibn al-Qalanisi told it. They said you could test a Damascus blade by placing a silk pillow on its edge and letting it fall. The pillow would be sliced in two by its own weight. Another story said a sword could be so sharp it could split a single hair dropped on it, lengthwise. This wasn't myth-making, it was a documented observation. Consistent, a technological gap so wide it felt like magic. The ore came from a real, tangible superiority. These weapons represented a paradox. It defied the understanding of the era. A metal that was flexible enough to avoid shattering and hard enough to cleave through almost anything. That reputation forged trade routes. It shifted the balance of power. The legend was earned on the anvil of conflict. And that performance, that historically recorded performance, sets the stage for the mystery. If the legends are true, and the accounts suggest they are, then what we're looking for isn't a lost art. It's a lost science, a science so advanced the blades it produced became the benchmark for a millennium. And now we're finally asking the right questions about the patterns in the steel. The final, perfect blade marked the end of an era. The forges in Damascus and other places, they went quiet, not suddenly but slowly, a fade. By the 18th century, the knowledge was just evaporating. The master smiths, they were the last ones who knew. They passed on without writing anything down. Their techniques were locked in a guild system, all oral tradition, strict secrecy. When they were gone, the silence was absolute. The formula for that legendary steel vanished, as if it never existed, a vanishing act on a civilizational scale. But why? What could cause a loss that total? It wasn't one event. It was a perfect storm of change. First, the lifeblood dried up. The unique ore, Wootz, it came from specific mines in India and Sri Lanka. Its composition was special, rich in trace elements. That was crucial, but trade routes are fragile. Political shifts, new conflicts, the ebb and flow of empires, it disrupted the supply. You can't make a masterpiece without the right clay. Then, the world's priorities changed. The age of the knight and the sword was giving way to the age of the gun. Warfare evolved. The immense skill and time for one Damascus blade became less practical. When you could arm a regiment with muskets, the economic incentive to preserve this art, it just faded away. And the knowledge itself was its own enemy, held in strict secrecy, passed only from master to apprentice. It was a flame that needed constant tending. One broken chain, one generation without a worthy student, and the light went out forever. A historian compared it to losing the formula for Roman concrete. A functional masterpiece, a pinnacle of practical science, just slipped through the fingers of time. That disappearance is what changes these blades. From beautiful artifacts into profound riddles, they are questions made of metal, and that makes the modern investigation more than metallurgy. It becomes a race. A quiet urgency to reclaim a piece of our collective intellect before the clues themselves turn to dust. And the first real clue, the one that broke the case open, was hiding in plain sight. In the most iconic feature of the blades themselves. Those steel cakes were the Rosetta Stone, Wootz ingots. They didn't look like a legendary weapon. A rough, dark gray puck, about the size of a small loaf of bread, with a surface that shimmered with tiny crystalline speckles, that was the raw material. For centuries, they were forged in southern India, a sophisticated crucible process, a secret in itself, then shipped thousands of miles across the Indian Ocean up through Persia to the forges of Damascus. The smiths there didn't start with iron ore. They started with this pre-made high-carbon steel cake. That was the first genius move, beginning with a superior ingredient. But what was in it? Modern analysis shows Wootz wasn't just steel. It was an engineered alloy soup, very high carbon content, around 1.5%. And laced with trace impurities, tiny amounts, vanadium, molybdenum, chromium. These weren't contaminants, they were crucial catalysts from the unique ores of those specific Indian mines. European blacksmiths later, when they got Wootz ingots, failed spectacularly. They would melt the ingot down, try to work it with their traditional European methods. The result was always a disappointment, a brittle, useless bar of steel, no beautiful pattern. They assumed the secret was in the chemical recipe alone. They were wrong. The ingot wasn't the recipe, it was the seed. You can have a packet of seeds for a magnificent, ancient tree, but if you throw them on concrete, nothing happens. The seed has the genetic blueprint, but it needs the exact right conditions, soil, water, temperature, to express that blueprint. The Wootz ingot was that seed. Its unique crystalline structure, forged in those Indian crucibles, contained the geometric potential. Those trace elements acted like guides, pinning the carbon into specific arrangements during the slow, controlled cooling. They created a microscopic landscape, cementite, a very hard iron carbide, arranged in bands or particles within a softer steel matrix. This was the pre-installed pattern. Waiting in code, the Damascus smith's job wasn't to invent the pattern. It was to decode it, to use heat and hammer to unfold that hidden geometry, to pull it up from the microscopic world and etch it across the surface of a sword. So the European failure proved a point. The magic wasn't in the ingredient list you could write down. It was in the transformative process that followed. The ingot was a locked box, and the key was a secret dance of fire and force, one we are only now beginning to understand. Damascus steel, its genius isn't about adding something. It's about revealing what's already there. That pattern, the swirling like smoke or water, that's not decoration. It's a window. You polish the blade, wash it with a mild acid. The surface changes. The acid reacts differently to the two microstructures in the metal. It etches one away a bit more, and what comes out is a map. A topographical map, a portrait, really, of the steel's soul. Every curve, every band of light and dark, it all corresponds to the internal architecture. This is where the art becomes engineering. The dark lines are bands of an incredibly hard compound, cementite, iron carbide. The lighter areas are the softer steel matrix. More flexible, together they form a natural laminate, a composite material. Think of it like plywood, but on a microscopic scale, even nanoscopic. layers of a hard substance suspended in a tough, forgiving base. That structure is the source of the legendary properties. The hard cementite bands give the edge its sharpness, its ability to hold that edge. The softer steel matrix absorbs impact. It keeps the blade from shattering. It's the perfect marriage, hardness and toughness, a compromise that had eluded smiths for centuries. But how did these layers form? The smith didn't paint them in. He coaxed them out through a precise ritual of heat and hammer. It began with the Wootz ingot. The smith would heat it to a very specific temperature. A glowing orange, not white hot. Then, with controlled strikes, he'd begin to draw it out into a bar. He'd fold it over upon itself, weld it shut, twist it. Draw it out again. This wasn't random pounding. It was a geometric algorithm, performed with muscle and fire. Each fold multiplied the layers. Each twist created complex, swirling interfaces. The key was maintaining that precise thermal window. Too hot, and the delicate cementite structures would dissolve back into the steel, destroying the pattern's potential. Too cold, and the metal would crack. The smith was working blind, guided only by the color of the glow and the feel of the hammer. His manipulations did something extraordinary. They physically aligned and stretched the nanoscale components already seated in the Wootz. The trace elements acted like signposts, guiding the carbon to form into these bands and particles as the metal was worked. So the final pattern is a fossil, a permanent record of every fold, every twist, every draw. It's the visible signature of an invisible process, a bridge between an artisan's intuition and the organized chaos of the nanoscale world. The smith wasn't just making a sword, he was conducting an orchestra of atoms, directing them into a structure of sublime performance. But if that structure was invisible, how could we ever see it? How could we prove what was really there? The answer would come from a tool the ancients could never have dreamed of. The hammer stopped, the steel kept its secrets. For almost 200 years they were invisible. Then, in the late 20th century, we built a new kind of eye, one that could see in nanometers. The Electron microscope. It let scientists do something new, to stop guessing about Damascus steel, to finally look, to go past the pattern on the surface, to go into the metal itself. When researchers put a piece of an old blade under that power, the image was revolutionary. It was a landscape, a world of order. What they saw were structures so advanced they defied every assumption. Woven through the steel were carbon nanotubes, perfect cylinders of carbon atoms. A honeycomb lattice, the same nanotubes we make today in billion-dollar labs, and next to them nanowires of cementite, the hard compound that gave the blades their edge. This was the proof. These weren't accidents, they were deliberate, a nano-architecture built by the ancient process. The Wootz ingot had the recipe, carbon and trace elements. The smith's forging provided the energy, the thermal cycling. Together, they guided the carbon atoms. They arranged themselves into these strong, tiny structures during the slow cooling. Think of it like building the world's strongest rope. You wouldn't use a thick hemp cord. You'd weave thousands of microscopic carbon fibers. The Damascus smiths did the equivalent. They grew those reinforcing fibers from within the metal as it formed. The carbon nanotubes acted like microscopic rebar. When a crack tried to start in the blade from an impact, it would hit these tiny, tough cylinders. The nanotubes would stop the crack or force it to change direction, dissipating the energy that gave the steel its combination of hardness and flexibility. It could hold a razor edge because the cementite nanowires provided a hard surface, and it wouldn't shatter because the nanotube mesh held everything together. Like a safety net at the atomic scale, the implication is staggering. Centuries before we had the word atom, blacksmiths were manipulating matter at that scale. They were practicing nanotechnology, not with clean rooms, but with charcoal fires and hammers, an intuition honed by generations. Their goal was a superior sword. Unknowingly, they built a nanocomposite material, a link between the forges of the ancient world and 21st century science. The mystery was no longer just what they made, but how they could have known, which leads to the question, was it knowledge or was it something else, a hidden intelligence in the process itself? The answer was in the dirt. The specific dirt from southern India and Sri Lanka. Modern metallurgists, they had pure iron, measured carbon. They could make a pattern, but the steel was weak. It didn't have that resilience. The magic wasn't in the main ingredients. It was the trace elements, the impurities, vanadium, molybdenum, maybe some tungsten. Things present in such tiny amounts, they were just seen as contaminants, but they were directing everything at the nanoscale. They were like a catalyst. You only need a speck. Without it, nothing happens. In the Wootz ingot, these elements did two things. First, they helped form the hard cementite bands. They acted like a template, guiding the carbon atoms to line up in specific ways during the ingot's slow cooling over days in the crucible. Second, they guided the self-assembly of the carbon nanotubes. The excess carbon in that high-carbon steel needed a path, a scaffold to grow on. These trace impurities provided that scaffold. They lowered the energy needed for the carbon atoms to arrange themselves into those perfect, strong cylinders. Modern science has an analogy. It's called doping. In semiconductors, you introduce a tiny amount of a foreign element into ultra-pure silicon. That one impurity, atom in a million, it transforms the material's electrical properties. It turns an insulator into the foundation of a computer chip. The ancient Indian smelters, the Damascus forgers, they were doing the same thing. They were doping their steel, unknowingly using the unique geological fingerprint of their ore to engineer the material at the atomic level. That changes the story. The lost formula wasn't just human instructions. It was a partnership, a dance between human skill and a specific gift from the earth. You couldn't write the recipe on a scroll because part of the recipe was the land itself. The mines that produced that ore are exhausted now. Their precise geochemical signature is lost, so the legendary blades, they're not just artifacts. They're geological artifacts. Each one contains a map of a specific hill, a specific vein of ore that's gone. So recreating it isn't just about rediscovering a technique. It's about reverse engineering a piece of the ancient world's chemistry, and that leads to the final variable, the one the smith controlled with his eyes, his instinct. The fire was the final step. The smith controlled it with a deep understanding of heat. Not just high heat, but a precise thermal dance, a ritual of temperature and time. The Wootz ingot, with its special recipe, was inert. It needed the exact right sequence of energy to unlock what was inside. That was the lost heart of the craft. The critical thermal cycle. Think of it like baking a delicate soufflé. You have perfect ingredients, eggs, flour, air. But if the oven is too hot or you open the door too soon, it collapses. The structure fails. The Damascus process was that sensitive. The smith would heat the steel to a specific orange glow, not white hot, which would be too violent. Research suggests a precise window between 800 and 900 degrees Celsius. Then came the slow part, the opposite of what you might expect. Instead of quenching the red-hot steel in water to harden it fast, they did something counterintuitive. They cooled it slowly, often over days. This process is called annealing. Or in this specific context, cycle forging. They might heat it, then let it cool in the forge ashes, or bury it in insulating sand. This gentle, prolonged cooling was everything. It gave time for the magic to happen at the atomic level. During that slow cool down, the excess carbon in the steel couldn't stay dissolved. It had to come out. Like sugar crystallizing from a slowly cooling syrup, the trace impurities, the vanadium and molybdenum, acted as gathering points, nucleation sites. They gave the carbon atoms a blueprint, a place to arrange. So as the steel cooled over hours and days, the carbon precipitated out. It formed into those hard bands of cementite. And under the guidance of those trace elements, some of the carbon did something extraordinary. It curled, atom by atom. It linked into perfect hexagonal rings, then rolled into tiny, incredibly strong cylinders. Carbon nanotubes, the slow cooling provided the calm, controlled environment for this nanoscale self-organization to occur. If they had cooled it quickly by quenching, the carbon would have been trapped in a different, disordered structure. The result would be hard but brittle, useless for a sword that needed to flex. The smiths, through generations of observation, discovered this precise temperature recipe. They didn't know about atoms or nucleation. They knew by the color of the metal, by the way it felt under the hammer, by the quality of the final etch. They had an empirical mastery of phase transformations. They knew that this specific slow dance of fire and time turned a lump of metal into something transcendent. It was a technology of patience, an understanding that sometimes to create ultimate strength, you must apply the gentlest touch. This thermal knowledge was the most fragile part of the chain. The easiest to lose, and when it was gone, the seed of the Wootz ingot found no soil to grow in. The symphony had its score, but the conductor was gone. So we are left with a question. If they achieved this without microscopes or chemistry textbooks, what were they really doing? Was it just trial and error? Or was it something closer to an art form, a deep dialogue with the material itself? He never saw a molecule, never knew the word atom. His lab was the forger's glow. His instruments were a hammer, an anvil. His data was the color of the metal and the sound of the strike. A master smith working in the dark, and with every fold, every precise heating, he was running one of the most sophisticated material science experiments in history. An unknowing nanotechnologist, his goal was simple, a sword that wouldn't break, a blade that held an edge, but to get there, he manipulated variables with a precision that would make a modern engineer stop. The color of the heat, a deep cherry red versus a bright orange, that was his temperature gauge. The ring of the hammer, a dull thud meant the metal was too cold. A sharp ping meant it was ready. That was his feedback on the internal structure, the count of the folds, the rhythm of the draws. This was his algorithm. He didn't have a checklist. He had a tradition honed over generations, a deep, tactile conversation with the material itself. He would say the steel was talking to him. And in a real sense it was. He was creating the conditions, the perfect, gentle thermal cycles, the precise mechanical working, all to coax the steel into showing its hidden potential. He was building the stage, but the performance at the atomic level happened on its own. The carbon nanotubes self-assembled. The cementite nanowires grew along the pathways he forged. He didn't place them there. He made the world so inviting that they couldn't form any other way. His skill was environmental design, crafting a tiny universe of heat and pressure where the laws of physics naturally assembled a masterpiece. A researcher once described it perfectly. They were playing with atoms, they just didn't know it, and this reframes the entire loss. We didn't just misplace a recipe. We lost a language, a non-verbal, intuitive understanding between human hands and elemental behavior. The knowledge was in the muscles, in the eyes, in the subtle feel of the hammer bouncing back. It was a feel for the material, an artistry of cause and effect that was never written down because it was lived. This is why modern attempts at recreation are so fascinating and so difficult. We have the electron microscopes, we have the chemical spectrometers, we can see the nanotubes they created, but we are trying to quantify an intuition. We are trying to translate a feeling into data points. We can make steel with a pattern that looks like Damascus, but replicating that performance, that perfect marriage of hardness and flexibility, requires us to learn not just what they did, but how they knew when to stop. How they listened. The true secret might not have been in the fire itself, but in the centuries of quiet attention that taught them how to hear its song. The labs trying to recreate Damascus steel, they're a kind of bridge. They're not forges, they're rooms with machines, electron microscopes, spectrometers. Computer-controlled furnaces. Scientists and historians work together. Their goal isn't just a replica, it's to crack an ancient code, to understand the sequence so well they can program it. They start with the evidence, the blades, using tools like synchrotrons, particle accelerators that make incredibly bright light. They can scan a historical blade. They map its internal structure in 3 dimensions. They find every trace element down to parts per million. That gives them the blueprint, the what. Then comes the harder part, the how. They have to source ores that match the ancient geological fingerprint. They have to smelt their own Wootz in crucibles, controlling the cooling over days. Then they have to forge it. Here, the high-tech meets the ancient. Some teams use furnaces with digital controls, programmed to follow a precise thermal cycle. They heat the steel to exactly 850 degrees Celsius. They hold it there for a precise time. Then they cool it at maybe 10 degrees per hour. They're trying to automate the intuition of the master smith, and they've had successes. They can produce steel with a beautiful, swirling pattern. Tests show it's superior to ordinary modern steel. It holds an edge better. It has more flexibility, but a debate continues. Have they truly matched the ancient nanostructure? The carbon nanotube networks in the lab-made steel are often shorter, less organized. The cementite bands might be there, but the intricate laminate might not be as perfect. The difference is subtle, but it's telling. It suggests the computer program, for all its precision, might still be missing a variable. Maybe it's the human touch, the slight variations in hammer strikes, the intuitive adjustment to a draft in the forge, the feel that tells a smith the metal is ready, not when a timer goes off, but when the glow is just right. These replication projects are a form of historical detective work. They force modern scientists to think like ancient artisans, to ask not just what the recipe was, but why each step was necessary. Every failed batch, every blade that cracks or shows a weak pattern, is a clue. It tells them what not to do, and each small success brings them closer to the mind of the smith. This whole endeavor shows a gap. We know in detail what the ancient smiths achieved. We can see their nanotechnology, but knowing exactly how they did it with charcoal, bellows, and a hammer, that's the deeper puzzle. And solving it requires understanding not just their actions, but the remarkable benefits those actions yielded. What did those nanostructures actually do for the sword? The answer is in the physics of the edge itself. The edge of a Damascus blade under a microscope wasn't smooth. It was a landscape. Those dark bands, the cementite, they were harder. So as you used the blade, they wore down a little less. They'd stand just a bit higher than the steel around them. That created a natural serration, a microscopic saw. Which is why the stories talk about it cutting a piece of falling silk. A smooth edge might push a fiber aside, but a saw with all those tiny teeth, it catches the fiber. It slices through, but that serrated edge is only part of it. The real trick was keeping that edge, because any metal, when you stress it, deforms. Its internal structure develops flaws. Dislocations, they move, and when too many pile up in one place, the metal bends, or a crack starts. For a sword, that means the edge dulls, it rolls over. The carbon nanotubes in the steel stopped that. Think of the metal structure like a brick wall. The dislocations are cracks moving through the mortar. Now put in countless, incredibly strong carbon fibers, running through the wall in every direction. When a crack tries to spread, it hits one of these nanotubes. The nanotube is bonded to the steel. It stops the crack, forces it to go around. The energy dissipates. In terms of the metal, the nanotubes pin the dislocations. They anchor the lattice, so the edge is incredibly difficult to deform. You could sharpen it to a razor's edge, and it wouldn't just fold over on the first impact. The nanostructure held it there. That's edge retention. In a time when most swords needed constant care, a blade that could last a battle and still be sharp. That was a real advantage. It turned the weapon into something reliable. A warrior could trust it not to fail. That alone would have built the legend, but it was paired with another ability. The same nanostructure that made the edge so hard, it also gave the blade a kind of flexibility. That flexibility is the second miracle. A blade that hard, one that can cut armor, should be brittle. It should be like glass, but the stories say these swords could be bent almost in half, and then they'd snap back straight. That wasn't magic. It was a material compromise engineered at a scale the smiths couldn't see. The secret is the steel's composite nature. You can think of it like a suspension bridge. The cementite bands are the hard steel cables. They give you the tensile strength. The softer steel matrix is the flexible roadway. It gives way a little and it distributes the load, and the carbon nanotubes are the microscopic ties. They connect the cables to the deck, they transfer stress, they hold it all together. So when a huge force bends the blade, the energy doesn't concentrate in one spot. It travels, it dissipates along all those interfaces between the hard cementite and the soft steel. It runs along the length of the nanotubes, which are incredibly strong in tension. So you don't get a single catastrophic crack. The energy is shared. It's spread out across millions of tiny structural elements. The blade yields, it flexes. But it doesn't break, and because the steel matrix is elastic, once the force is gone, it pulls everything back into shape. That property, that combination of hardness and the ability to absorb energy, is called toughness. It's the holy grail for any material. For a sword, it meant survival. In the chaos of a fight, a parry against a heavy blow, a strike against a shield that could warp or shatter an ordinary blade. A Damascus sword could take that impact. It could bend to absorb the shock and spring back ready. That toughness came from the nanoscale architecture. The smiths, with their thermal cycling and forging, weren't just making a pattern. They were building a microscopic damage control system. They made a material where failure had to work incredibly hard to happen. Every potential crack faced a labyrinth. It would hit a nanotube and be deflected. It would reach an interface and have its energy bled away. This is why modern materials scientists study these blades with such reverence. We design composites, carbon fiber polymers, metal matrix composites with the exact same goal: to combine different materials to get properties neither has alone. The Damascus smiths did it 1,000 years ago. They built a composite from the inside out, growing the reinforcing fibers within the metal itself. Their success was so complete the weapon seemed to possess a kind of life. A resilience that felt supernatural, but it was just physics orchestrated with an artisan's unknowing precision. And that leaves the final question. If they could achieve this without any of our knowledge, what does that say about discovery? Was it all accidental? Or is there a deeper kind of knowing, written not in books, but in the silent language of fire and iron? The pattern told the truth. After that final etch, the smith would see the soul of his work laid bare. Those swirling lines of light and dark, they weren't just for beauty. They were a diagnostic, a living report card on the whole process. A clear, sharp pattern with high contrast between the dark bands and the lighter steel that was the sign of success. It meant the thermal cycles had been perfect. The slow cooling gave the carbon and trace elements time to arrange themselves, to form those organized, reinforcing nanostructures. The bands were long and unbroken, which meant the cementite had formed in continuous layers, and the carbon nanotube networks were well developed throughout the metal. That blade would ring true. It would hold an edge, it would flex without fear, but a blurry pattern or one with gaps and broken lines, that was a warning. It signaled a flaw. Maybe the temperature spiked too high at one point, dissolving some of the delicate nanostructures, or the cooling was too fast, preventing the full self-assembly. Or the mechanical working was uneven, failing to properly align the internal geometry. That blade, while it might still look impressive to an untrained eye, would have weak points. In a brutal test, it would be the one to fail. So for the master smith, the moment of etching was one of profound tension. He was reading the material's history. The pattern revealed everything: the care with the fire, the consistency of the hammer strikes, the purity of the original ingot, and the most aesthetically stunning blades, the ones with those hypnotic, watery patterns. They were almost always the pinnacle of performance. The beauty wasn't separate from the function. It was the function made visible. This unity, it's a profound idea from the ancient world. It suggests that in certain high crafts, aesthetic excellence isn't an added luxury. It's the external signature of internal perfection. The smiths didn't add beauty to a functional object. They perfected the function, and beauty emerged as a natural byproduct. It was a form of truth in materials, and this principle, it might be a key to understanding other lost technologies. Where we see artifacts of stunning artistry and complexity, we should ask not just how they were made, but what their beauty is telling us. What it says about the sophistication of the process that created them. The pattern was a language, and in its elegant script was written the whole story. From the chemistry of the earth to the final strike of the hammer, the ultimate test is simple. How does Damascus steel compare to the metal in your car or a modern scalpel? It's a question of context. Today we have steels that are engineering marvels, alloys with names like maraging steel, tool steel. They're products of immense control. We start with iron of near-perfect purity. Then we add precise amounts of chromium, nickel, molybdenum, vanadium. We control the chemistry to the 0.1%. Then we subject them to advanced heat treatments, quenching in oil or salt baths, tempering at exact temperatures for precise times. The result is a material with staggering, reliable properties. A modern high-performance alloy can be made harder than any historical Damascus blade. It can have a tensile strength that dwarfs it. In a head-to-head test of pure numbers, the modern alloy wins. It's the product of centuries of science, of laboratories and quality control. But that comparison misses the point. It's like comparing a hand-built wooden sailing ship to a nuclear aircraft carrier. The carrier is objectively more powerful, more capable, but the ship is a work of art built with an intimate knowledge of wind and wood. Its genius is in its relationship with natural forces. Damascus steel is that ship. The ancient smiths began not with pure iron, but with an impure, variable ore. Their furnace was a clay pot and a charcoal fire. Their thermometer was their eyes. Their quality control was the sound of the hammer and the final etch. They had no periodic table, no concept of carbon nanotubes. Yet, through a process refined by generations, they coaxed a nanocomposite material from the chaos. They used the natural impurities in the ore not as contaminants, but as essential catalysts. They didn't add reinforcing fibers, they grew them from within. The elegance is breathtaking. They achieved a multi-functional material, hard, tough, flexible, through a beautifully simple, integrated process. Modern engineering often achieves performance by adding complexity. More alloys, more steps, more energy. The Damascus approach was about elegant efficiency. A system that turned limitations into advantages. In this way, the ancient blades are not obsolete. They are prophetic. They foreshadow the entire field of modern composite materials. Think of carbon fiber reinforced polymers. We take strong carbon fibers and embed them in a plastic resin to create something both light and incredibly strong. The Damascus smiths did the equivalent inside a piece of steel. Their cementite bands and carbon nanotubes were the reinforcement. The softer steel was the matrix. They built a composite from the atoms up. Their work also hints at biomimicry and self-assembly. In nature, complex structures like bone or seashells aren't forged in a furnace. They grow guided by biological templates. Damascus steel, in a way, grew its own nanostructure. The slow thermal cycles and trace elements guided the carbon into organizing itself. This is a powerful idea for sustainable engineering today. Could we design materials that assemble themselves with minimal energy, using common elements the way life does? The Damascus smiths, in their pursuit of the perfect sword, may have shown us a path, so the comparison isn't about which material is better. It's about recognizing two different kinds of brilliance. One is the brilliance of total control and precision. The other is the brilliance of harmony, of working with nature's own tendencies to elicit extraordinary performance. One tells us how far we've come. The other reminds us of a different kind of knowledge we may have left behind, and that raises a final possibility. If this one secret was lost for centuries, what other elegant solutions from the past are waiting to be rediscovered? They didn't know they were making carbon nanotubes, almost certainly not. They had no idea about atoms or molecules, engineering something 1,000,000 times smaller than a grain of sand. That idea wouldn't have made any sense to them. But they did it, and they did it consistently for centuries. That's the paradox. It makes you ask what discovery even means. The Smiths weren't trying to make nanotechnology. Their goal was practical. A sword that wouldn't break, one that held a sharp edge that showed that watery pattern. That was the target. Every adjustment to their process, every refinement passed down, was aimed at that outcome. The fire had to be this color, the ingot had to cool this slowly, the hammer had to strike in this rhythm. They were perfecting a recipe, a method of fire and force. The nanoscale architecture, the nanotubes and nanowires, that wasn't the goal. It was the hidden mechanism, the invisible engine that made the visible excellence possible. Think of it like baking perfect sourdough bread, centuries before anyone discovered yeast. A baker would keep a starter passed down. They'd know that feeding it rye flour made the bread rise better. They knew the exact feel of the dough, the right oven temperature, the sound the crust made when it was done. They could make a magnificent, airy loaf every single time. But they had no idea their success depended on trillions of microscopic fungi and bacteria. Their knowledge was in the process, in the sensory feedback. In the consistent result, the science of microbiology came later to explain why that old method worked. The Damascus smiths were in the same position. They were master bakers of steel. Their hands-on knowledge was so deep, so refined through trial and error, that they consistently created the precise conditions. The right heat gradients, the chemical environment, the mechanical stress, conditions that coaxed carbon atoms into forming nanotubes. It was a side effect, but a non-negotiable one. Without that nanostructure, the sword wouldn't have had its legendary properties. So was it an accident, not a lucky fluke? It was the systematic, repeatable outcome of a perfected craft. It's a stunning example of a principle, technology preceding science. Human beings are brilliant toolmakers, brilliant pattern recognizers. We can develop sophisticated methods to achieve an outcome long before we understand the underlying principles. We can build a bridge that stands without a full theory of engineering. We can ferment drinks without knowing chemistry. The Damascus smiths built a nanocomposite material through the school of trial, error, and observation. Their discovery wasn't of the nanotube itself, but of the entire chain of cause and effect that produced it. That blurs the line we draw between accident and discovery. It suggests that deep, attentive engagement with the material world can lead to advanced technology, even without formal theory. The Smiths may not have known what they were making at the atomic level, but they knew with absolute certainty how to make it. Their knowledge was encoded in action, not explanation, and that invites a wider question. If this level of sophistication could be achieved and then lost, what other capabilities from our past are waiting in plain sight, their true mechanisms still hidden behind the veil of practical mastery? The Industrial Revolution needed sameness, steam, interchangeable parts, production lines. When the great powers of the 19th century armed their massive armies, they remembered the legend. They wanted that legendary steel for their cavalry sabers. Factories were told to recreate Damascus blades, not by the dozen, by the tens of thousands. It was the first serious scientific attempt to get the secret back, and it failed completely. The sabers they made were serviceable, strong enough for combat. But they were ordinary, no special edge, no supernatural flexibility. The beautiful pattern was often there, etched on the surface, but it was a facade. That attempt showed the fourth clue in the mystery, maybe the most telling one. The things that made Damascus steel a masterpiece were the exact things the new industrial world couldn't copy. The problem started at the source. The factories didn't have the original Wootz ingots. The Indian mines were exhausted. They used ores from Europe or America. And those ores lacked the critical trace impurities: vanadium, molybdenum, tungsten. Without that unique geological fingerprint, the seed for the nanostructure was missing. You can't grow an oak tree from a hazelnut. They were trying to bake the legendary soufflé with different eggs. Then the process. Industrial forges were built for speed and volume. The idea of heating steel and letting it cool slowly over days, maybe in a bed of ashes, that was anathema to mass production economics. Time was money. So they used faster methods. They often used a technique we now call pattern welding. That's what many people today mistakenly call Damascus steel. You take layers of different steel, a high carbon and a low carbon iron, fold them together again and again, then etch the surface to reveal the pattern. The result can be stunning, a beautiful wood grain effect, but it's a mechanical laminate. It's like making plywood by gluing thin sheets together. True Damascus steel from Wootz was a grown laminate. Its structure formed from within during that slow thermal dance. The factory-made pattern-welded steel lacked the self-assembled nanocrystalline heart. No carbon nanotubes, no cementite nanowires, a clever imitation of the surface with none of the internal engineering. This failure is revealing. It tells us the lost technology wasn't a single trick. Not a step you could write in a manual. It was a holistic system, a fragile ecosystem of cause and effect. It needed a specific material, the Wootz ingot. It needed a specific, patient process of thermal cycling, more like gardening than manufacturing. And it needed the artisanal skill to read the metal, to make micro-adjustments based on feel and sight. The Industrial Revolution excelled at standardizing the variable. It sought to remove the artisan's intuition and replace it with a machine's repeatability. But here, the artisan's intuition was the machine. The system valued speed and uniformity. Damascus steel was the antithesis. It was slow, and each blade was subtly unique, a product of its specific journey in the forge. The factories could make a good sword, but they could not make that sword. The attempt proved the legend was built on something more than a formula. It was built on a harmony of elements that the modern world, in its rush forward, had left behind. Which raises a thought. In our own pursuit of efficiency and scale, what other forms of deep material wisdom have we designed out of existence? That ancient blade isn't just in a museum anymore. It's in labs. Scientists are taking it apart, not for swords, but to solve problems we have now. The most direct use is in new composite metals. Think about an aircraft part or something in a high-performance car. You always want it stronger, lighter, more durable, and Damascus steel is a blueprint for that. They're trying to copy its self-assembled nanostructure in modern alloys. The idea is to put carbon nanotubes into molten metal on purpose, hoping they'll spread out and line up during the process, the way they did in the forge. If that works, you get metals with a phenomenal strength-to-weight ratio, materials that are incredibly tough, but light enough to change transportation and aerospace. That sword is a 1,000-year-old proof that such a material is possible. and that it can be supremely functional. But maybe the bigger lesson is in the method. The self-assembling part today, making advanced composites, is complex. It takes a lot of energy. We build things layer by layer, or we mix components with great force. The Damascus process suggests a different path. It shows that under the right conditions, the right heat, the right catalysts, a material can organize itself. From the inside out, that's a principle for smart materials. Scientists are looking at alloys that, during heat treatment, will naturally develop internal patterns. This could mean more efficient production, less waste. Instead of forcing a structure, you cultivate it. Then there's the role of the trace impurities. The ancient smiths didn't purify their ore. They used its natural fingerprint. Those tiny amounts of vanadium and molybdenum acted as catalysts. They directed the entire nano-architecture with minimal input. For sustainable design now, that's a crucial insight. It points toward using minimal strategic additives. Instead of loading a material with rare elements, you might use a tiny, precise amount of a catalyst to trigger the change you want. That's potentially cheaper and more environmentally sound. So what does a modern engineer learn from an ancient sword? They learn that elegance often beats brute force. That a deep understanding of process can defy the limits of the starting ingredients. The blade is a testament to a different kind of material intelligence. One born from observation, patience, a dialogue with nature's own tendencies. It guides research away from just adding complexity toward more elegant solutions. The future of materials science might not be a new element on the periodic table. It might be in rediscovering the wisdom of an old, patterned piece of steel. And that journey makes you ask a final question. What does losing and finding such a secret say about us, about our relationship with the knowledge of the past? The legend has this weight to it, and it's cast its own shadow. A kind of fog, really half-truths, romantic stories that can blur what was actually achieved. So first, a distinction that matters. What you usually see now, sold as Damascus steel, that's pattern welding. It's a skilled craft, a beautiful one. A smith takes two different steels, stacks them, heats them, hammers them together, folds the billet again and again. When you etch it, you see these layers like wood grain. It's a tribute. It honors the aesthetic of those old blades, but it's not the same as true Damascus, forged from a single Wootz ingot. The modern version is a mechanical laminate, layers fused. The ancient version was a grown laminate, its structure coming from within. Both are impressive, but they're different. One imitates the effect, the other grew it from atomic principles. Then the idea of an unbreakable sword, that's a fantasy. The accounts are clear. These were superior weapons, but not invincible. A chronicler might praise a blade that bent and sprang back, but they also noted a poor one, or one struck wrong, could shatter. They were tools of war, subject to brutal physics. Their legend comes from being remarkably reliable, not magical. That actually makes their performance more credible. The stories of flexibility are likely true, but they describe a peak achievement, not a universal rule, and the secret was never one mystical ingredient. No dragon's blood, no metal from stars. Meteoritic iron was used in some ancient weapons, but not here. The romance of a lost recipe is compelling, but it oversimplifies. The power wasn't in one thing you could add, it was in an entire system. The specific ore with its trace elements, the crucible process to make Wootz, the precise thermal cycling, the skilled mechanical work. It was a chain of cause and effect, a symphony, not a single note. Looking for a magic bullet misses the point. The genius was in the process itself. And those beautiful patterns, sometimes it's said a warrior could recognize his smith's work by the swirls in battle. A poetic idea, but unlikely as a primary function. The pattern was a byproduct, a diagnostic. It was the visible signature of a successful internal nanostructure. The smith used it to judge his own work, to see if the thermal cycles were correct. Its beauty was a side effect of getting the material science right. Function made art. Debunking these myths, it sharpens the appreciation. When you strip away the fantasy of unbreakable swords and magic recipes, what's left is more astounding. Real people with charcoal fires and hammers developed a process so sophisticated it manipulated matter at the nanoscale. The truth isn't less wonderful than the legend. It's more profound. It replaces magic with a deeper marvel, human ingenuity, expressed through generations of silent, attentive craft, and that truth invites a final look. Not just at the blade, but at our own relationship with forgotten knowledge. What this whole journey of loss and rediscovery tells us about progress and about what we might still overlook in our own world. A Damascus blade made a statement. It spoke before you ever drew it. In the courts of sultans, the halls of kings, these swords were the ultimate gift. They weren't just weapons, they were objects of immense prestige. You gave one to cement an alliance, to acknowledge power, to secure a favor. To give one was to offer a piece of the pinnacle of known technology. To receive one was an acknowledgement of your status. The sword symbolized more than strength. It represented wealth because only the richest could commission one. It represented technological prowess, a mastery over nature few cultures could claim, and it represented a connection to trade networks that spanned continents. That cultural weight transformed it. The blade became an artifact of soft power. A caliph might send one to a Byzantine emperor, a message forged in steel. It said, "Look what our artisans can do. Look at the reach of our commerce." The object itself was an ambassador, carrying a civilization's reputation in its etched pattern. That reputation was built on an economic engine of astonishing scale. The journey of a single sword was a map of the medieval world. It began in specific mines in southern India and Sri Lanka, where ore with that crucial geochemical signature was dug. That raw material was smelted into Wootz ingots in local crucibles. These heavy cakes of steel then traveled thousands of miles, by ship across the Indian Ocean, then overland through Persia. They arrived at the forges of Damascus, of Aleppo, where master smiths performed their art. The finished blade might travel further, west to the markets of Cairo, across North Africa, north into Anatolia, the Black Sea regions, or to the trading posts of Venice, from where it could find a European noble, a knight returning from the Crusades. This wasn't a simple trade good. It was a high-value, low-bulk luxury item, perfect for long-distance trade. It fueled merchants, supported ports, enriched cities. Damascus itself became synonymous with this peak of craftsmanship. Its name, attached to the steel, elevated the city's status for centuries. It was a brand long before the concept existed. A guarantee of quality known from India to England. When the technology was lost, the ripple effects were profound. It wasn't just that a way of making swords disappeared. A major export industry, one that defined a city and a region, diminished. The cultural symbol that had represented Islamic technological achievement for centuries faded. The void was both economic and symbolic. A key strand in the web of long-distance trade was severed, and the world lost a tangible, functional proof of a material science tradition, a height the modern era would not rediscover for hundreds of years. The blades were the peak expression of pre-industrial metallurgy. Their disappearance marked the quiet end of an era defined not by machines, but by intimate, artisanal mastery of material. Historians now look at trade ledgers, diplomatic correspondence, tracing the echoes of that loss. Scientists stare into electron microscopes, trying to rebuild that mastery from the atoms up. We are left striving to fill that void, not just with replica swords, but with an understanding of the holistic world that created them. A world where commerce, culture, and craft were woven together as tightly as the carbon nanotubes in the steel itself. And that pursuit leads to a final reflection on the nature of knowledge itself. The blade sits in a climate-controlled case. It's a masterpiece behind glass. For a scientist, it's also a locked archive. The question is how to read it without breaking the seal. This is forensic metallurgy. The investigation has to be as precise as the artifact. The first rule is do no harm. Museums are protective of these pieces of history. Every study starts with a careful negotiation. Researchers have to prove their methods are non-destructive. Or, when it's absolutely necessary, micro-destructive, taking a sample so tiny it's invisible to the naked eye. One of the most powerful tools is advanced imaging. Using specific wavelengths of light or raking light at a sharp angle, photographers can reveal surface details of the Damascus pattern. They can map variations that hint at the forging process. All without touching the metal, but to see inside, to read the steel's atomic diary, requires more. For a truly non-invasive look, scientists might use synchrotron radiation. That means taking the blade to a facility like a particle accelerator. Incredibly bright, focused X-rays are generated. The blade is scanned. The way the X-rays scatter or are absorbed creates a detailed three-dimensional map of its internal structure. It can reveal the distribution of different phases, the alignment of the cementite bands, even the presence of trace elements, all while the artifact stays completely intact. Sometimes, though, a microscopic sample is needed. With permission, a conservator might use a specialized drill. They remove a tiny fragment, often from the tang. The part of the blade hidden under the handle, where any removal is least impactful. This speck of metal, smaller than a grain of sand, becomes a world of data. Placed in a scanning electron microscope, an SEM, it's bombarded with electrons. The resulting images can show the nanostructure in breathtaking detail. The carbon nanotubes, the cementite nanowires, the grain boundaries of the steel, an attachment called an energy dispersive X-ray spectrometer, an EDS, can then tell scientists exactly what elements are present. And in what proportions. Each analysis like this is a collaboration. The historian provides context: where the blade was found, its likely age, its stylistic features. The metallurgist provides the hard data, the chemistry, the microstructure. Together they build a profile, and by comparing profiles from dozens of blades from different centuries and regions, a timeline begins to emerge. They can see the technology at its peak with consistent, well-developed nanostructures. They can identify blades from the decline, where the patterns are weaker. The chemistry slightly off, that suggests a breakdown in the supply chain, or a loss of precise thermal knowledge. A blade from the 17th century might show a beautiful pattern but a less organized internal composite. A sign that the art was being preserved aesthetically, but the deep science was already fading. This forensic approach transforms each sword. It's no longer just a weapon or an art object. It's a sealed data capsule. Its steel silently recorded the conditions of its creation, the heat of its specific forge, the skill of its smith, the unique fingerprint of its ore. For centuries, that data was unreadable. Now, with these delicate tools, we are learning its language. Each non-destructive scan, each microscopic sample, is like carefully turning a page in a book we thought was lost forever. And the story these blades are telling is not only about the past. It's a detailed technical report, a set of blueprints from a forgotten age of material genius. Waiting to inform the next, the steel didn't need a blueprint, it needed a guide. That's the fifth clue, seeing the process not as an invention, but as a kind of growth. You look to nature, bone forming in your body, a mollusk building its shell. These aren't built piece by piece, they're self-assembling systems. Organic templates create a scaffold. They guide minerals from the surrounding fluid. They deposit in precise, layered patterns. The result is a composite, astonishing strength. Bone combines flexible collagen with hard apatite crystals. Nacre, mother of pearl, stacks microscopic tablets of aragonite, a brick-and-mortar arrangement with organic glue. These are hierarchical structures, organized from the molecular level up, and they form not by force but by following simple rules under the right conditions. Damascus steel did something similar. But in a forge, the Wootz ingot with its trace impurities was the inorganic template. Elements like vanadium and molybdenum, they acted as nucleation sites. Gathering points, the slow, controlled thermal cycle set by the smith created the environment, like the mineral-rich fluid. Under those conditions, the excess carbon in the steel couldn't stay dissolved. It had to precipitate out, and it did. By following the template, the carbon atoms migrated to those impurity sites. They began to arrange themselves, forming the hard bands of cementite, and some, guided by the same atomic geography, linked into hexagonal rings, carbon nanotubes. The material organized itself. The smith didn't place every atom. He created the world where the atoms had no choice but to arrange into a masterpiece. His role shifted from creator to facilitator. From architect to gardener, he cultivated the conditions. The steel grew its own strength from within. This biological analogy, it's more than poetry. It reframes the achievement. It connects this ancient craft to a modern frontier. Biomimetics, scientists look to nature's designs, spider's silk, a lotus leaf surface. To solve human problems, the goal is to copy the principles, not the materials, to create things stronger, lighter, more efficient. Damascus steel is a historical precedent in that field. It shows hierarchical, self-assembled composites aren't exclusive to biology. They can be achieved in metallurgy, using heat and chemistry as the guiding forces. The implication is profound for how we design materials. Much of our manufacturing is top-down. Start with a bulk material, machine it, shape it, force it into form. The Damascus method, like nature's method, was bottom-up. It built complexity from simple components, letting organization emerge from the rules of the system. This suggests the most elegant designs come not from imposing our will on matter, but from understanding its inherent tendencies, creating the right stage for it to perform. The ancient smiths, pursuing a perfect sword, accidentally mastered a principle modern science is still striving to harness. They demonstrated that under the right guidance, materials possess a silent intelligence, a capacity to assemble into forms of breathtaking function. This perspective doesn't diminish their skill, it elevates it. Their genius was in learning to listen to the metal, to collaborate with the hidden laws of its nature. That biological perspective puts us at a modern crossroads. We're on the verge of unlocking the full sequence, of turning that ancient dance into a digital recipe, and that raises a quiet question: should we do it? There's an ethical tension here between two goals. One is preservation. The mystery of Damascus steel is itself a piece of cultural heritage. It's driven centuries of inquiry, of wonder. That sense of a lost pinnacle pushes science forward. It reminds us our ancestors achieved things we still can't fully explain. And some argue that solving the mystery completely might diminish that. It could turn a living legend into a lab report. The unknown has a power to inspire that the fully known sometimes loses. On the other side is the drive to recover, the scientific imperative to understand, and the deep respect of wanting to honor the ancient smiths by finally comprehending their full genius. This isn't about stealing a secret. It's about completing a conversation that was interrupted for hundreds of years. And the potential benefits are tangible. A fully recreated process could lead to new materials, more sustainable manufacturing. It could validate entire fields of study focused on self-assembly. So recovering this knowledge could be seen as a duty, a reclaiming of a thread of human ingenuity that was severed. This debate extends into the practical realm. If a research team using modern tools finally cracks the code and can reliably produce the steel, what then? How should that knowledge be shared? Does it become proprietary, patented for profit? Or is it treated as recovered human heritage, published openly for all? There's a powerful argument that something born from centuries of anonymous, collective craftsmanship belongs to humanity, not to a single entity. But the realities of research funding and intellectual property are complex. These aren't just technical questions, they're philosophical ones. They force us to examine our relationship with the past. Are some secrets meant to stay lost, their value lying in the quest they inspire rather than the answer they yield? Or is our responsibility to reclaim every piece of our intellectual history, to leave no discovery buried? This debate grows more pressing. Our analytical tools grow ever more powerful, capable of dissecting history at the atomic scale. The choice of what to resurrect and how to steward that resurrection is becoming a recurring theme. It asks us to consider not only what we can recover, but what we should. And that introspection leads us to look beyond a single blade, to wonder what other echoes of lost mastery might still be whispering to us from the artifacts of history. That blade's legacy isn't just in the past anymore. Its principles are becoming a blueprint for a new material age. Think of a bridge spanning a great river. Its steel cables could be woven with carbon nanotubes, grown right into the metal during fabrication. Those microscopic reinforcements would make the structure incredibly strong and lighter, allowing for longer, more graceful spans. And because the nanostructure mimics that ancient composite, it could have a kind of resilience. Self-healing. When a microscopic fatigue crack starts from stress, the aligned nanotubes and the composite matrix could redistribute the force, blunt the crack's progress. It wouldn't magically repair like skin, but it would dramatically slow failure, giving engineers years of warning. This isn't fantasy, it's active research. Inspired directly by the multifunctional performance of those historical swords, the applications go far beyond construction. Consider space exploration. Every gram matters. A spacecraft hull or a lander's leg, made from a modern alloy engineered with Damascus-like principles, it could be phenomenally tough and lightweight. It would need to withstand extreme temperature swings, micrometeoroid impacts, immense launch forces. A material that combines hardness and flexibility at the atomic level is the ideal candidate. Researchers are exploring metal matrix composites, where carbon nanotubes or other nano-reinforcements are intentionally dispersed, guided to self-assemble using thermal processes. Processes that echo the ancient cycle forging. The goal is to grow strength from within, just as the Wootz ingot did. Perhaps the most profound future is in the human body. Medical implants, joint replacements, bone plates, they face a constant challenge. They must be strong enough to bear load, but also biocompatible, resistant to fatigue. A material that mimics the hierarchical, forgiving structure of Damascus steel, and maybe bone itself, could be revolutionary. Imagine an implant whose nano-architecture encourages bone cells to integrate with it, forming a seamless bond. Its inherent toughness would mean it could last a lifetime without the risk of sudden, brittle fracture. Those ancient smiths, in their pursuit of the perfect weapon, may have inadvertently outlined the design for the perfect biomedical material. This future vision ties to a shift in how we make things. The traditional industrial model is often linear, energy-intensive. We extract, refine, alloy, and shape with force. The Damascus process suggests a more elegant path, sustainable. It shows that by understanding and harnessing self-organization, by creating the right conditions for a material to find its own optimal structure, we might use fewer rare elements. Less energy. Manufacturing could become more like cultivation. This approach aligns with green materials science, which seeks to reduce environmental impact at every stage. The lost method points toward a future where we don't dominate materials, but collaborate with their intrinsic properties, so the story of Damascus steel is completing an arc. It began as a pinnacle of ancient craft, faded into legend, was resurrected as a scientific mystery, and is now emerging as a wellspring of inspiration. Its ultimate legacy is a mindset. It teaches that the most advanced solutions aren't always found in the newest lab. Sometimes they are waiting in the quiet wisdom of an empirical past. In objects that achieved sophistication through deep observation and patience, this rediscovery is forging a new dialogue, where an archaeologist's careful cataloging and a materials scientist's atomic probe are part of the same conversation. It proves that looking back with the right tools and the right questions can be the most forward-thinking act of all. The forge still glows. You find it in workshops, not labs. In sheds and barns, backyard studios, that's where the modern bladesmith works. Scientists are looking for the atomic blueprint. These artisans are keeping the flame alive. Their hammers are a personal quest to connect through fire and metal to an ancient standard. Most work with pattern welding now, layering different steels. Creating that swirling visual tribute, they aren't recreating the nanostructure of true Damascus, but they are mastering the ancient language of the forge. The precise heat control, the rhythmic folding, the patient drawing of the steel, and then the final etch. They study historical pieces, not with microscopes. With their eyes and hands, learning the flow of the patterns, the heft of a finished blade, the goal is to capture the spirit, that marriage of beauty and rugged function. Every billet of steel is a conversation with history. Each fold is a step in a ritual, passed down now through shared knowledge, online forums, the quiet mentorship of a craft community. They experiment different steel combinations, different folding patterns, etching techniques, a ladder pattern, a raindrop, a twist. Each one is an attempt to echo the old masters. To understand the decisions made at the anvil 1,000 years ago, their work is a living tribute. It values the human element, the eye judging the color of the heat, the hand feeling the steel's resistance, the intuition that knows when to strike and when to let the metal rest. In an age of mass production, this dedication to the singular object is a statement. It says some knowledge can't be digitized. It has to be lived, practiced, felt. These modern blades aren't historical replicas, not in a strict scientific sense. But they are something just as important. They are a tangible connection. They ensure the legend isn't just a story in a book. It's something you can hold. Feel its balance. See the dance of light on the etched surface. These smiths are preserving a cultural memory, a standard of craftsmanship. It compels us to make things well. With care and intention, they remind us, before a technology becomes a formula, it is first an art. And that art, kept alive by passionate hands, continues to inspire. It bridges centuries, the human drive to create objects of utility and beauty. That's a flame that never truly goes out. It started with a sword, a legendary blade. And it ends here with a microscope, with the hum of electrons. We went from myth to molecule, from stories of battles to the actual blueprint, the atomic structure. The lost nanotechnology in Damascus steel. It's not a complete mystery anymore. It's been revealed. It stands as a testament to human ingenuity, an ingenuity so deep it mastered the nanoscale centuries before we even had that word. That's the core of it. It wasn't magic. It was a material symphony played with charcoal and a hammer. There are three key things. First, the recipe. It wasn't just any ore. It was ore from specific ancient mines in India with a unique geological fingerprint full of trace catalysts. Second, the thermal dance. The slow, precise cycles of heating and cooling that gave the atoms time and direction to arrange themselves. And third, the self-assembly, the carbon nanotubes and nanowires that grew from within, creating a composite of incredible toughness and resilience. Together, these elements forged a material that defied the understood limits of its time. This story does more than solve a puzzle. It challenges how we see things. It asks us to look at other enigmas with new eyes. The Antikythera mechanism. Roman concrete that lasts millennia. The mysterious strength of Viking Ulfbert swords. Could these be waiting for us to ask the right questions? To look not just at the object but into its hidden architecture. It urges us to value that deep intersection, where art and intimate craft and emergent science become the same thing. Where beauty isn't applied, it emerges as the signature of perfect function, moving forward into our own age of wonders. Let that Damascus blade be a reminder. The most elegant solutions are often hidden in plain sight. They wait not in the distant future, but in the quiet wisdom of the past. They just need the right perspective to uncover them.